In this video, we focus on engineering functional surfaces, bridging materials with chemistry and biology to advance regenerative medicine. When designing medical devices, whether implantable like bone plates or external like biosensors, one key goal is to ensure they interact meaningfully with the biological environment. Most medical devices are sized in millimeters to centimeters, but the interactions that determine their success happen on a much smaller scale. A single human or animal cell is only 10 to 100 micrometers, while biomolecules like proteins or enzymes are even smaller, measured in nanometers or angstroms. That's where biofunctionalization comes in. It's the process of modifying a material's surface so it can interact specifically with cells or biomolecules. This allows devices to do more than just sit in the body. They can guide healing, trigger responses, or detect precise signals. To make this work, we engineer surfaces across multiple scales. At the microscale, features influence how cells attach, spread, and migrate. This is relevant in tissue engineering and regenerative implants. At the nanoscale, we reach membrane proteins like integrins, which are responsible for how cells anchor to surfaces and sense their environment. Surfaces may also be designed to capture biomolecules, such as those used in diagnostic sensors. At the angstrom level, specific molecular interactions occur. For example, a peptide like RGD fitting into a receptor's active site. These interactions are stabilized by metal ions like magnesium at what's called the MIDAS domain, acting as a docking point that ensures proper recognition and attachment. And finally, at the femtometer scale, atomic-level properties such as ionic charge, binding energy, spatial orientation, and crystal structure determine whether these molecular interactions are attractive, repulsive, or perfectly matched. By engineering surface features at these fine scales, both physical and biochemical, we can design devices that communicate with the body, respond effectively, and perform with precision. Biofunctionalization is the process of modifying a material's surface so it can interact with biological systems, like molecules, cells, or tissues. In diagnostics, we use it to detect specific targets in samples like saliva or blood. Surfaces are functionalized with chemical groups or biomolecules like antibodies to improve specificity. When the target binds, it creates a measurable signal, called transduction, which might be optical, electrochemical, or physical. In implants, we're not detecting anything. Instead, biofunctionalization helps guide cell responses. For example, by presenting peptides or growth factors that encourage healing or reduce inflammation. And in drug delivery, the goal isn't to detect the drug, but to deliver it effectively. We functionalize the carrier surface to help it find the right target, like a specific cell type or tissue, or to respond to cues such as pH or enzymes, releasing the drug at the right time and place. So whether for sensing, healing, or targeted delivery, biofunctionalization makes materials smarter in how they interact with the body. Before we functionalize a surface, we first choose the base material. This choice affects how we clean it, modify it, and how it interacts with cells, biomolecules, or drugs. Here's a list of common base materials used in diagnostics, implants, and drug delivery. Depending on the ultimate goal, we might use a single material, or combine materials, like using metal for strength, and adding a ceramic or polymer coating to improve biocompatibility, control cell behavior, or guide drug release. When you're working at the micro or nanoscale, even the tiniest speck of dust or oil becomes massive. And it can interfere with how your medical device performs. That's why proper cleaning is crucial before any surface modification or biofunctionalization. Let's start with dry cleaning methods like UV/ozone and plasma cleaning. These use reactive gases such as oxygen, air, hydrogen, or argon to remove organic or carbon-based dirt. UV/ozone cleaning is milder, while plasma cleaning can chemically react with surface contaminants. But be careful. Physical ablation may occur if argon gas is used. Argon is heavier and can physically damage sensitive patterns or coatings on your surface. Alternative to dry cleaning is wet cleaning. These methods involve strong chemical solutions to dissolve, etch, or lift away contaminants. Piranha solution is powerful but harsh. It removes stubborn organics and even changes the surface itself. RCA cleaning, commonly used in semiconductor labs, is a bit more controlled. It comes in two steps. One removes organics, the other targets metals and ions, all while protecting delicate materials like glass or silicon. Note, if you're working with nanoparticles in suspension, these types of surface cleanings don't apply. You'll want to focus on solvent rinsing or other liquid phase purification techniques specific to your application. When preparing materials like metals and glass for medical devices, we often use alkaline cleaning and acid passivation. Alkaline cleaning removes grease, oils, or machining residues using solutions like sodium hydroxide, usually warm, to lift off contaminants. Then, acid passivation, using nitric or citric acid, helps strip surface contaminants like metal ions and promotes the formation of a stable oxide layer. This boosts corrosion resistance and biocompatibility, key for implantable materials. Cleaning methods depend on context. In research labs, the focus is on precision, so harsh methods like Piranha or RCA are common despite being time-consuming. But in industrial manufacturing, the goal shifts to safety, scalability, and cost efficiency. That's why alkaline cleaning and acid passivation are often used. Dry cleaning methods like plasma or UV/ozone are also common in industry, especially when surfaces are sensitive or moisture needs to be avoided. Ultimately, the choice depends on material, purpose, budget, and regulatory requirements. Once the cleaning step is done, how do we know if the surface is actually clean and ready for the next process? That's where post-cleaning tests come in. We usually look at both physical and chemical properties. For physical checks, a goniometer measures wettability, how easily water spreads on the surface. A cleaner surface is often more hydrophilic, which helps with molecule or cell attachment. Then there's AFM, or atomic force microscopy. It creates a nanoscale 3D map of the surface so we can visualize roughness, texture, and any remaining contaminants. On the chemical side, XPS, X-ray photoelectron spectroscopy, tells us which elements are present and their chemical states, but only within the top 5 to 10 nanometers. TOFSIMS, or time-of-flight secondary ion mass spectrometry, is even more detailed. In surface mode, it analyses just the top 1 to 2 nanometers, but with depth profiling, it can go hundreds of nanometers deep, or even up to a few micrometers, depending on the material and sputtering conditions. Lastly, AES, Auger electron spectroscopy, is highly surface-specific. It detects elemental composition in just the top 2 to 5 nanometers. It's often integrated into scanning electron microscopes, or SEM, but uses its own detector system and operates in ultra-high vacuum. Together, these tools confirm whether your surface is truly clean or if it needs further treatment before moving on to functionalization. It's quiz time. Stuck? No worries. Pause the video, check back on the previous slides, or feel free to Google it.